test. All right, new topic today, Gibbs free energy. Gibbs free energy is indicated with the thermodynamic letter G, delta G. And what Gibbs free energy basically is the amount of energy free to do work. So when a reaction happens and we utilize that in the form of heat or energy, Gibbs free energy will tell us that amount available. Gibbs free energy can be found two different ways. We can find Gibbs free energy with Big Mama, but what's different about delta G than about H and S is delta G is very temperature dependent. So you can only use Big Mama at room temperature, which is how many Kelvin? 298 Kelvin. Normally, you end up having a non-standard temperature, and even if you do have a standard temperature, we can utilize and solve Big Mama for delta H and S, which are not as temperature dependent, plug them into this equation and solve for delta G. This is known as the Getto-Homey take speed equation. You all remember this from Chem 1? Okay, so this calculation and the calculation of delta G in any way is our second way to determine if something is spontaneous or thermodynamically favored. If a reaction has a negative delta G, that means it is spontaneous. Is this pen too light? Delta G means that it is spontaneous or thermodynamically favored. So there's only two ways to determine if a reaction is thermodynamically favored. One using Getto-Homeys. What's the other way? No, we did it yesterday to find if something's spontaneous. Delta S of the universe. Okay, those are two calculations that you can do. You can't just look at delta H alone or delta S alone of the system to determine spontaneity. You can only look at delta G or delta S of the universe. Does everyone get that? That's really, really important. So again, here we have the Big Mama. Just remember, if you do Big Mama, you can only do Big Mama with delta G at 298 K. Super temperature dependent. If not, we will then go to Getto-Homeys. So what we care about when we're dealing with Getto-Homeys is primarily when will something become spontaneous? At what temperatures? Because our temperature is the thing we can control. H and S is set, but we can vary temperatures and make reactions occur and not occur. So this table is a table of all the different combinations of H and S and at what temperatures spontaneity would happen. Some people subscribe, some teachers subscribe to the idea of, oh, they need to memorize this. I do not want you to memorize this, okay? What I'm going to do now, and you might need to find some space in your notes and write Getto-Homeys 4 times, I'm just going to take you through the 4 scenarios, and we'll talk about at what temperatures it would be required in those scenarios to make these reactions spontaneous. So our options will be, when we're looking at what temperatures, we're not looking for a specific temperature, we're looking for a range. So a reaction, when we're talking about this, is either spontaneous at high temperatures, at low temperatures, all temperatures, or never spontaneous. Those are going to be the 4 possibilities for these. So let's take a look. Again, if we want spontaneity, what is the sign of delta G? Negative. So we're looking at what temperatures would be required in, let's do an exothermic reaction with an increase in entropy. Let's start with that one. If I have an exothermic reaction, what is the value of delta H? Negative. If I have an increase in entropy, what's the value of delta S? Positive. So keeping in mind that we're on the Kelvin scale, so all temperatures are positive, right? Don't worry about signage on that. At what temperatures would this reaction maintain a negative delta G? All temperatures. Do you see why? Because I have a negative value here, and I keep subtracting off from that negative value. So no matter what I start with, it's always going to stay and become more and more negative, no matter what temperature I put in there. Does everybody get that? So in this combination, we are spontaneous at all temperatures. I don't feel you need to memorize this. You're going to be given a set of conditions in a question, and just look at Getto-Homeys. and answer it that way. You don't need to memorize. You guys are good enough at math that this should not be an issue. All right, so now let's do a different set of conditions. Let's say it's exothermic with a decrease in entropy. Exo means, what's delta H? Negative. A decrease in entropy means delta S is negative. So remember, our goal is to have a negative delta G. What does a minus a negative mean? We're actually going to add it, right? So I'm going to do the plus plus thing here. So, at what temperatures can we keep delta G negative? High temperatures, low temperatures, or never? Low, exactly. We are starting with a negative term, and we want to keep this last term small enough so the positive doesn't overtake that negative. So therefore, this is spontaneous at low temps. Okay, let's look at our next set of conditions. Let's go ahead and do endothermic with an increase in entropy. What is the sign of delta H when we're endothermic? Positive. And what's the sign of delta S when we have an increase of entropy? Positive. All right, so if we want this to be a negative or a spontaneous reaction, what do we need that temperature to be? High. By it being super high, this negative term can then overtake this positive. So this is spontaneous. And again, that also means I'll write thermodynamically favored because that's how you're going to see it. But I don't want to write that every time because I'm lazy. At high temps. Okay, our last one needs to be endothermic with a decrease in entropy. So endothermic is positive, decrease in entropy, negative. So we get a minus minus again, right? So I'm going to do that, make that a plus. What's the deal here? This is never spontaneous. Test, test. My mic just cracked and it's freaking me out. All right, so again, don't memorize them. You know, I don't think it's a bad idea to know when the always and nevers are, and those are kind of easy to remember. When is something going to always be spontaneous? Exothermic, increase of disorder. That kind of makes sense. We're releasing a lot of heat, and we have an increase in disorder. And then the never, when's never? Endothermic, decrease. The other two you can definitely figure out when they give you the problem, so don't memorize it. Okay, let's move on to some problems. We're going to calculate delta G of this reaction. It's the one we worked on yesterday when we found delta H and delta S for the following. And because it says this little delta G naught, that means it's at standard conditions. So that technically means we're at 298 K. So with that being the case, how do we want to solve for this? We're going to use Big Mama, and we're actually going to do it two different ways. We're going to solve with Big Mama, and you have the values on question number 1 from yesterday. So y'all will have to give me those values. In question number 1, delta G is equal to, what was my delta G value? I'm doing products minus reactants for aluminum chloride. Negative 629. All right, products minus, and then free elements all have delta G's as 0. So that would be 0. So my value from Big Mama is negative 629 kilojoules per mole. Does everybody agree with that? Don't be quiet. I yelled at first period because they were too quiet. I'm not playing this game. We good? Okay. So now we're going to use Ghetto Homies and prove that we will get the same answer. you guys already calculated delta H and delta S. So from problem number 1, what was your delta H value with units? 704? Yeah, that's right. The S was the 2-something. 704 kilojoules per mole. And then your delta S, negative 252 joules per mole K. Because I want to compare to the other delta G, I'm going to go ahead and change this. Normally I change to joules, but I'll change this one to kilojoules just because I want to compare. And herein lies the biggest mistake students make on Big Mama. They leave these. They don't care about units. Students just plug in and solve like it's super easy. You can't do that with different units, okay? You got to be in the same one. So we're going to find delta H, write it down as negative 704 minus, what was our temperature? 298 times negative 0.252. And both of these are in kilojoules per mole. And this one is kilojoules per mole K. My K's are going to cancel, leaving me with my answer in kilojoules per mole. And tell me what you get. Negative 629. Looky there. So just know that you can always use Ghetto Homies. You can't always use Big Mama with delta G. So no harm in doing this other than the fact it's a little bit extra work because you have to use Big Mama to find 2 things as opposed to just one. Are we good? All right, moving onward. Now we're going to calculate the temperature at which this reaction occurs spontaneously. Okay. To deal with this, we have to understand that there's a point at which we turn from spontaneous to non-spontaneous, or we turn from non-spontaneous to spontaneous in the world of temperature. All right? So at that exact point, when we're either going to go positive or negative, what is the value of delta G? Yeah, think about a number line. If we have a 0, this is the cusp that exists between spontaneity or thermodynamic favorability and not. So to find the temperature at that point, what do you think we're going to do? Any ideas? Plug a 0 into Ghetto Homies for which thing? Delta G. But what about, we got to solve for temperature. What about the other stuff? We use Big Mama to find H and S, and then we'll plug in and solve for temperature. Okay, so we're actually only going to do this twice today. It's cumbersome, but I need you all to get practice with making sure your units are right and all that jazz. So I have all the numbers on the board, so we can plug them in. Let's first do delta H. NH4Cl's delta H, thank you, is negative 313.43. Minus HCl, and there's only one of all of these, so 1 times HCl, is that gas? Yes, negative 92.307 plus NH3 gas is negative 46.11. So what is our delta H? I need a couple people to make sure we have the right answer. Negative 175? All right, I saw a couple heads nod, so that's negative 175 kilojoules per mole. Because I want to convert everything to joules, because I like to do that, I'm going to do this right now and make it negative 175,000 joules per mole. Get it out of the way right away so it won't be so daunting later when you have to go plug stuff in. Because when you're done, I know you just want to immediately plug stuff in. By doing this now, it keeps you in check. So delta S's value, we've got 94.6 for the ammonium chloride entropy. Ugh, silly dyslexia. Joules per mole K minus 1 times HCl, 186.908. plus an H3 of 192.45. Okay, so what is our delta S? No decimal, one decimal place for this one. How about that? That one should have had 2 decimal places. Oh well, that's fine. What, does anyone have this in their calculator still? 0.01? Okay, so it should be 175,010. Just joules per mole. Okay, that's what we're going to use. And then this one should have 1 decimal place. Delta S is negative 284.8 joules per mole. Does everyone agree a second on that number? Yes. All right. So now we can go ahead. We have our H and our S. We're going to plug them into this equation. Delta G is equal to negative 175,010 joules per mole minus temperature is what we're looking for. And our delta S is negative 284.8. And this is going to give us the value of, yes, I was just about to write K here and realized it wasn't there. Okay, K is in the unit our temperature will come out at. And what is that temperature? .614. We're going to leave it at 615 Kelvin because we have a no decimal place number minus a whatever. Don't worry too much about sig figs. Got it? Just a lot of math. I don't think conceptually it's that hard. It's watching your units, all that kind of stuff, plugging in, double checking your work, making sure you calculate it correctly. So it's pretty hot. So in these problems, we don't need to do math, but we need to look at ghetto homies to figure out what happens if we increase temperature. What happens to delta G? Does it become more spontaneous or less spontaneous? Does it become more positive or more negative? And that's what we're going to look at. So delta G is equal to delta H minus T delta S. We really don't need to know what the delta H is to answer this question because the temperature is what's changing. So that's only going to affect this second term. So it's going to get more positive or less positive regardless of what delta H is. Does that make sense? So let's take a look at, so the only thing we need to really concern ourselves with is what? Delta S. So looking at this reaction up here, we have solid and liquid going to solid. What is the sign on that delta S? Negative. So if this is negative, we do our plus plus thing. If we increase temperature, what happens to our delta G? Increases. You can say, so there's 3 different things you could say. Delta G increases. Delta G becomes more positive, or you could say delta G becomes, in terms of spontaneity, what is it? Less spontaneous. Any of those will work. If they say value, how does delta G, in my opinion, that question, all of those are okay. If they say the numerical value, this third one I don't think would be appropriate. Okay? All right. Next one. Same situation. We're going to see what a temperature change will do to the spontaneity of this. So what is my enthalpy here? We said positive. Why is that? We went from 1 moles of gas to 2 moles of gas. That's an increase in entropy. So that is a positive delta S. So what does an increase in temperature do to this? Delta G decreases, D-R-E-A-S-E-S, or delta G becomes more negative, or delta G becomes more spontaneous. All right, and the last one's going to be, we have both cases here, so we can copy down one of them, but based on entropy, what happens to this entropy? It increases. We're going from 2 moles of liquid and a gas to 3 moles of gas. That's definitely an increase, so this is going to be positive. So these answers are the same here. Okay? All right. Only 2 more problems. Next one's going to be a pain, but it's going to be worth it because it's going to be interesting. So you have on number 10, you've got 3 parts. We're only going to do the first part because you're going to need a lot of room because the calculating of the delta H's and delta S's is a little more taxing because the numbers are bigger and we have more to do. For each of the reactions listed, I basically just want you to tell me what temperature it's going to be spontaneous. So again, how do we set it up? We're going to use our ghetto homies, and what are we going to do? Set delta G 0, because that's at the point where positive becomes negative or negative becomes positive. Delta H and S, I'm going to have to use ghetto homies, and I am solving for T ultimately, correct? So this is just going to be a pain, but everything's on the board. So delta H is equal to 1 times CO2 is on the bottom, negative 393.504. .509, thank you, plus 2 times H2O gas is negative 241.818. Those are products, minus methane, 1 times negative 74.81, plus 2 times O2 we know is going to be 0. And I forgot to mention this. The reason I chose this reaction, what is this reaction? What kind of reaction is it? Combustion. More specifically, what are we combusting? Yeah, what is that hydrocarbon? Methane. We know that that's methane gas that comes out of our jets back there, right? So if I open up the jet now, is it going to combust? Is the reaction going to happen? No. What we're doing is finding at what temperature would it happen? What temperature would it have to be for that to occur spontaneously? So we'll see how far away from room temperature we're going to be to make this go. What is our delta H? 0.9? I didn't hear you. Negative 802.3. This is delta H, so that's kilojoules per mole. So I'm going to immediately change this to joules. Negative 802.300 joules per mole. And then delta S. Here we go. 1 times CO2 is 213.74. Plus 2 times water gas, 188.825, minus reactants, methane is 186.264. Is it 264? That's 624 in my head, it switched. And then 2 times O2, which is not 0 in the entropy world, 205.138. Oh, I needed 2. 205.138. So, what is my delta S? Let's crunch your numbers. Negative 5.15 joules per mole. That sounds familiar. Did anyone else get that? Okay. So now that we have our values, we're going to set everything equal. I just wanted the 0 to move. We'll just do it again down here. 0 is equal to delta H is negative 802,300 minus T times negative 5.15 joules per mole K. All right, so what is our temperature? Wow, that's going to be a... So are we safe? Pretty safe. Okay. All right, any questions about this? It's a pain, but you can see where all the student mistakes are going to be. It's in the math. It's in the conversions. It's in number crunching. So just be really careful. Always double check your answers. So the last one, which is my favorite, is this. We're going to use thermodynamics to find the boiling point of water. It's pretty cool. We all know the answer to this. What is the answer to this? 100 degrees Celsius. So let's go ahead and see if we can use thermodynamics to prove it as well. So if I am boiling water, I'm in a phase change. So if I'm in a phase change, what phase am I changing from? From liquid to gas. What's really, there's a couple points here that are crucial. First, when you have a phase change, that means you're at equilibrium. In a phase change, you've done that. You've done the heating curves in Chem 1 where you're at equilibrium when you're on that flat part of the curve. You've seen butt diagrams where you're on the curve itself. That's an equilibrium between the two states. What else is important is if you're at equilibrium, are you spontaneous in the forward or the reverse direction? Both are happening, right? So what does that mean then? Where are we in terms of delta G? 0. At equilibrium, delta G is 0 because you're both forward and reverse are happening. If your delta G were negative, only the forward would be happening. If your delta G were positive, only the reverse would be happening. But both are happening, so we're 0. So knowing this, how am I going to find the boiling point? We just did it. Delta G equals 0. We're going to put in ghetto homies, and we're going to have to solve for our delta H's and our delta S's, which are easy because it's just a number minus a number. So 0 is going to be equal to, let's find our delta H. So we do gas minus liquid. So water gases delta H is negative 241.818 minus the liquid negative 285.83 minus a negative. That's like plus. And what is our delta H? Say again? 44.01 kilojoules per mole. So what do y'all want me to do with that? Let's go ahead and get it in joules inmediatamente. Did you check out that Spanish? That was impressive. All right. So now we're going to go find our delta S. Our delta S is solid minus liquid. Our delta S is, where is my not solid, gas minus liquid. I was looking for solid. I'm like, where the hell is solid? Gas minus liquid, 188.825. Gas minus liquid of 69.91. So my delta S is 118 joules per mole K. All right, so now we can plug these in. We have 44,010 minus temperature times 118.9. Bless you. $370 what? 370 Kelvin. What's that in Celsius? I kind of want 1 sig fig. What's our boiling point? So I know y'all are perfectionists. Like, that 97 is not 100. You have to realize what backdoor engineering we're doing to find this boiling point. Delta H and delta S are somewhat temperature dependent. So they're not going to be exactly the same at 298 as they are at 100. Okay, a little bit, but not a ton. And then we're doing a ton of rounding, where different tables have different number of decimals. The fact we got that, that's pretty stinking amazing, in my opinion. But anyway, that is all. You can now work on your homework for 10 whole minutes.